The action potential versus the graded potential. Okay. Okay. Let's talk about the strength of both of these. Let's compare the strength. Let's talk about the direction, the ability to sum, right, which we spoke about, the refractory period, the duration, and let's talk about the movement of ions, which ions are moving. All right. So the strength of the action potential versus the graded potential, how do we describe that? How do we differentiate that? What did we sort of say about the difference in the magnitude of these?
The graded potentials can be added up.
Okay, so that would be under summation. So we'll say the graded potentials have the ability to sum, right? So they can be added. All right, and we talked about spatial versus temporal summation. Can action potentials be summed? No, right? So there's no ability for summation with the action potential. What else? What else? Let's go back to that magnitude, the magnitude of the action potential versus the graded potential. Which of these was stronger and more sustainable? Versus which of these sort of dissipated as it traveled? The action potential has a stronger magnitude, right? So we're going to say stronger, right? And we know that it's also all or nothing, meaning after threshold, we're going to fire an action potential. It's going to have the same magnitude all the time, right? There's no grading. Whereas graded potentials are weak and they dissipate over time. Okay. What about the direction of both of these potentials? What about the direction of change? Anyone? What about the direction of change? Are these excitatory, inhibitory? Are they both? Is it increase or decrease in the membrane potential change? Right. So that's the first thing here. The action potentials are always excitatory. Right, and this we call depolarization. Okay. Whereas graded potentials could either be excitatory, we'll say EPSB. All right, let's say excitatory or inhibitory, which could be either depolarization or hyperpolarizing. Okay. What about the refractory periods? So we know that graded potentials have no refractory period. What are the two types of refractory periods for action potential? And how do they differ? We talked about this. There were two types of refractory periods for action potentials. Right, so those are the absolute and the relative. Which of these came first? Good, the absolute. So the absolute was first. First here, and then we'll put the second here. Okay. And what was the reason for the absolute refractive period?
Sodium inactivation gates are closed.
Good, perfect. So the inactivation gate, oops, I'll say closed. So the inactivation gates on the sodium channels are closed, so we cannot depolarize this membrane. There's that brief period right after the action potential where it's impossible to fire another action potential. What about the relative refractory period? We can fire an action potential here, it's just harder. And this is because potassium channels are still trying to close. And it becomes harder for an action potential, right? So potassium channels are closing and it's harder for an action potential here. So you could potentially depolarize the membrane, it would just be much more difficult. I hope you guys can see that, it's a bit scratchy. All right, the last two categories here are the duration and the ion movement. So we know the duration of a graded potential is much more brief, so we'll say a few milliseconds. Right? They don't maintain for very long, whereas action potentials are about 1 to 2 milliseconds. And then what about the ion movements? Which ions are moving? What are the main ions moving for an action potential? Only sodium and potassium. Perfect. Only sodium and potassium. For the graded potentials, we have different ion movements. So it could be sodium, chloride, calcium, potassium, right? So all the other ions are moving for graded potentials, depending on if it's excitatory or inhibitory. Whereas for the action potential, only the movement of sodium and potassium are relevant.